Hello friends, in today's question, a black body is at a temperature of 2880 Kelvin. The energy of radiation emitted by this body with wavelength between 499 nanometer and 500 nanometer is U1, and between 999 nanometer and 1000 nanometer is U2, and between 1499 and 1500 nanometer is U3. The Wien's constant is given also, and we have to find out which of this option will be true. So basically it means that whether V1 or V3 is equal to 0, and what is the relationship between U1 and U2. So in this case we are going to use two formulas. One is called as a Planck's radiation law and another one is called as a Wien's law. And so let us start with the Planck's radiation law. Which gives us that the intensity of radiation at a wavelength of lambda intensity of radiation at wavelength lambda it is given as I lambda wavelength with respect to temperature is proportional to 1 upon lambda 5 and ratio of 1 divided by e raised to power hc divided by lambda kt minus 1, where this h is the Planck's constant h is the Planck's constant, c is the speed of light, and k is the Boltzmann constant, and T is the temperature. Second law which we are going to use is our Wien's law, and Wien's law gives us the peak wavelength, okay, or it is also called as a Wien's displacement law. Wien's displacement law, and this gives us the peak wavelength. So we can say the peak means maximum wavelength if represented as lambda max, this will be equal to B divided by T, and value of B is given and the temperature is also given, so we can find out that our lambda max is equal to 2.88 10 raised to power 6 divided by 2880, and this comes as 1000 nanometers. It means the radiation of intensity peaks at this particular value of the wavelength. So we can say from here that radiation intensity peaks at lambda max is equal to 1000 nanometers. So this is going to act as our reference. And now we are going to analyze the intensity radiation at the two wavelengths lambda 1 and lambda 2, where lambda will be our 499 nanometer and lambda 2 will be 999 nanometers. We say analyze radiation intensity at lambda 1 and lambda 2. So our lambda 1 is 499 nanometers. So from here we can easily see that the value of lambda 1 is much smaller than the maximum value of the wavelength. And from here we can also say, and it lies on the shorter wavelength side of the spectrum and lies on the shorter wavelength so which basically means high energy. Side of spectrum. So we can say that our intensity at wavelength lambda 1 for a temperature T is less than the intensity for the wavelength lambda max at the temperature T. So let us call this as equation number 1. Similarly, we can say that when lambda 2 is equal to 999 nanometer and this lambda 2 is fairly close to our lambda max. Therefore, we can write the relationship that our intensity for lambda 2 at a temperature T is close to for the intensity which is maximum wavelength. And let us call this as equation number 2. Now we can make a comparison between U1 and U2 which we are supposed to find out. Comparing U1 and U2. So the energy emitted in a small wavelength range, that is suppose delta lambda. So we can write the formula for that. The energy emitted in a small wavelength range it is given as U is proportional to the intensity at a wavelength, particular temperature, and multiply with the range of wavelength, where this delta L is our wavelength range, delta L. So from here we can say that our U1 is proportional to our I, that is our lambda 1 and T, and similarly we can write our U2 is proportional to I, wavelength lambda 2 and T. And if we make a comparison by using equation 1 and 2, using 1 and 2, we can easily say that our lambda so not lambda but intensity at wavelength lambda 2 temperature T is greater than the intensity at wavelength lambda 1 and temperature T. So this gives us that our U2 is greater than U1. So the options that are given to us is U2 is greater than U1. So option number D is the correct option. You can say option D is correct. So this completes the question. Thank you.